In part 4 of this chapter, we will look at thermal energy and the different units of temperature that we use when doing calculations in chemistry. So thermal energy is just going to be the constant random motion of material and matter. The atoms and the molecules that make up matter, we've said several times, they're never completely still, even in a solid. They're moving or vibrating around a fixed point. So they're constantly in a random motion pattern. And that motion converts to thermal energy. Now, thermal energy is expressed as the temperature of a substance. So it's just a measure of the amount of thermal energy when you're taking the temperature of something. The hotter an object is, the greater the motion of the atoms, the faster they're moving around, and the higher the temperature. There is a great way to kind of relate thermal energy to the motion of molecules using a graphic simulator that comes from the University of Colorado Boulder, and that link is on the Blackboard site under Chapter 3 Materials. It will also be in the Useful Links section, and we will probably take a look at that one in class as well. Now, be careful not to confuse heat and temperature. They are not the same thing. Heat will have a unit of energy on it. Okay, so remember your energy units, the calories, the joules, kilocalories. That is the transfer or exchange of thermal energy that is caused by a temperature difference. Okay, so an example of that is if you take a piece of ice and put it into a cup of warm water, there is more thermal energy in the water than in the ice. They're both water molecules, but the thermal energy is greater in the cup of warm water than it is in the ice cube. So you get a transfer of thermal energy. That is heat. Temperature is just the measurement of the thermal energy. So there's no exchange of thermal energy going on in temperature. It's simply a measurement. All right, so there are 3 temperature scales that you will see on a common basis. The one most people in the United States are most familiar with is the Fahrenheit temperature scale. And this is an arbitrary scale. It was designated that 32 degrees Fahrenheit would represent the freezing point of pure water, and that 212 degrees Fahrenheit would indicate, the boiling point of pure water. Now, we know that that can change depending on what's in the water. If you have a solution rather than pure water, you can have it freeze at lower than 32. That's how we melt ice in the winter on the roads. We put salt down and lower that freezing point, or if you put salt in your water, it has to get hotter to boil, but this is assuming pure water. Okay, so based on that, as we said, if we put something into water, like salt water, if you have a salt water body, such as, the sea, or you have some lakes that are salt water, those have to get a little colder in order to undergo phase transition, to go from a liquid to a solid, to reach the freezing point. So 0 degrees Fahrenheit has been designated as the freezing point of a saltwater solution. We know that normal body temperature, they're putting about 96 here. There's 98.6. That varies from individual to individual, but it is definitely somewhere up around closer to 100. Room temperature is usually designated as being about 72 degrees Fahrenheit. So these are all numbers you're probably pretty familiar with. Now, the other scale that you may be familiar with but not as familiar with is the Celsius scale. This is also an arbitrary scale. It was designated here that the freezing point of pure water would be 0 degrees Celsius, and the boiling point of pure water would be 100 degrees Celsius. Now, within this scale, Normal body temperature is about 37 degrees Celsius. So you can see that relationship between 98.6, 37, definitely a difference there. Room temperature is approximately 22 degrees Celsius as opposed to 74. So you can see that the Celsius scale is kind of in a shorter range of numbers. Again, they're going with the decimal scale from 0 to 100 rather than from 32 to 212. So there are 100 degrees difference between freezing and boiling on the Celsius scale as opposed to the 180 degrees on the Fahrenheit scale. And we'll look at the relationship between those in just a minute. But first, I want to look at a third temperature scale, and that is Kelvin. Now, Kelvin is the official SI unit for temperature, and this is designated as such because it is an absolute scale. It's not relative to anything else. It's not relative to the freezing point of water, the boiling point of water. It is an absolute measure of thermal energy. Absolute zero, 0 Kelvin, would be the temperature at which all molecular motion stops. Okay, now, we've never reached absolute zero just because we can never stop the motion of molecules, the internal motion of those. We can stop molecules from moving relative to one another pretty well, but there's always internal motion going on there that there is no way for us really to accomplish that. We can do it theoretically, but we've not accomplished that in reality. About the closest anyone has gotten has been about 4 degrees Kelvin. Okay, so 0 degrees Kelvin would be absolute ceasing of motion, absolute zero, coldest temperature possible. So according to that scale, the freezing point of pure water would be 273 Kelvin. The boiling point would be 373 Kelvin. It's relative in this sense to the Celsius scale in that there are 100 Kelvin units, Kelvin degrees difference there. Room temperature would be approximately 295 Kelvin. You may see some people say 298 Kelvin. It varies by a little bit. So if we look at how these three scales compare one to the other, the Fahrenheit degree is 5/9 the size of a Celsius degree. Okay, so that 5/9 comes back from that ratio. If you remember, I said that for the Celsius scale, there was 100 degrees, 0 to 100, and then on the Fahrenheit scale, there were 180 degrees. It went from 32 degrees up to 212. So if you take the ratio of 100 to 180 and reduce it down to the least common denominator for each of those, you get the 5/9. Okay, so here's the 100 degrees, here's the 180 degrees. The ratio of these to each other is 9 to 5 or 5 to 9 that way. Now if we look at Celsius and Kelvin, those track 1 to 1. The only difference is that for Kelvin, the 0 degrees is equivalent to 273, the 100 is equivalent to 373. So that makes conversion between Kelvin and Celsius very easy. Fahrenheit's a little more complicated. So here are the formulas. Degrees Kelvin is degrees, I'm sorry, I say degrees, there's no degrees because again, degree implies that it is a relative scale. It is absolute Kelvin. So we do not say degrees Kelvin, we just say Kelvin. Kelvin is equal to the degrees Celsius plus 273.15. In general, for any calculations we do, just the 273 is fine. Unless you need more significant figures, and we'll specify that, you can usually leave off the 0.15. Now to convert between Fahrenheit and Celsius, you've got this formula. Degrees Celsius is equal to the degrees Fahrenheit minus 32 divided by 1.8. Now I am not going to ask you to memorize this formula, this second one, for Celsius to Fahrenheit and vice versa. That is something that there are plenty of calculators and translators out there. I know even basic calculators now will usually have a function to convert between Celsius and Fahrenheit. You just start from one to the other, and certainly if you're using any sort of online application. You can look that up. So it's good to know the basic endpoints for Celsius and Fahrenheit and to be able to kind of compare those, knowing the difference between maybe room temperature or body temperature that are more relevant, but I will not expect you to memorize this one. It would be good for you to know how to apply the formula if you're given the formula and given one of these two temperatures. So if you need any help with doing those sorts of calculations, let me know. I'm not going to run through those here. You do need to memorize this first formula, the relationship between Kelvin and degrees Celsius. Now, if you're given degrees Celsius and you want Kelvin, you just plug it into this formula. If it's the other way around, if you're given Kelvin and you want to know what the degrees Celsius are, you're just going to flip this equation around. Subtract the 273.15 from both sides, so Kelvin minus 273 will give you your degrees Celsius. All right, now talking about thermal heat and temperature, we want to talk about another aspect of temperature and temperature change, which is the heat capacity of a substance. And heat capacity is simply the amount of heat, usually measured in joules, that you need in order to change the temperature of a particular substance by 1 degree Celsius, to either increase it or decrease it by 1 degree Celsius. Okay? It would also be by 1 Kelvin. And now heat capacity is going to be different depending on the substance that you're looking at. Each substance, each piece of matter, pure substances, will have its own heat capacity. So when you have an amount of substance and you express it in grams, the heat capacity would be known as the specific heat capacity. You may also see that abbreviated as SH or SHC. Also, it can just be abbreviated as the specific heat of a substance. That is telling you the amount of heat that you need to change the temperature, to raise the temperature by 1 degree generally. The units on that are joules per gram per degree Celsius, and it looks like this. So joule over grams, and then that grams is times degrees Celsius. So both of these go together. You could put parentheses around gram and degrees Celsius. Both of those are in the denominator. Joules is in the numerator. Okay. You could also put Kelvin here in place of degrees Celsius if necessary. You might have to do a conversion from Celsius to Kelvin. Now you have a list of some specific heat capacities in your textbook. This is table 3.4 from your book, and it just lists specific heat capacities of some of the more common substances, and there are thousands more than this. It's just a very short list of common items that you may come across. You can also think of the specific heat capacity as a substance's ability to just absorb and retain heat. So you can think of it in terms of something's ability to change temperature quickly or to not change temperature. So you can think of conductors and insulators a little bit in terms of specific heat capacity. And when I say conductor, I'm not talking conductor of electricity, I'm talking conductor of heat. So if you've ever seen thermal induction stovetops, this is something that you look at in terms of that. It's not the whole story, but it's part of it. Okay, so if we look at some of these substances, metals, lead, gold, silver, copper, iron, aluminum, there's something in common about all of those items. You've probably already noticed it. They are all metals. And what do we know about a metal's ability to absorb heat and release heat? We know that they're very good at absorbing heat quickly, but then they're also, relatively speaking, very good at releasing that heat and cooling down quickly. Okay? Now, some of them are better than others, so if we look down here, we've got aluminum, we've got iron, we've got copper, and then we've got silver, gold, and lead getting lower and lower and lower. Now, if we think about what these numbers mean, okay, so the amount of heat in joules per gram of that metal per degree Celsius. If we think about common uses of these, and we think about what we would use for, let's say, cook pots in the kitchen, which of these metals that are listed here are you more likely to see in those pots on the stove? It's not going to be lead, hopefully, not only because it's got a very low specific heat capacity, but also because it's toxic to us as humans. Gold and silver, yeah, they'd be really expensive to use, but they also have very low specific heat capacities, so they would heat up very quickly, but they wouldn't hold the heat on the food. Now, if you look at the next three, we've got copper, iron, and aluminum. Now, these are all three commonly found in cookware, and they are found in different pieces of cookware for different reasons. So copper is prized for its ability to quickly heat up and to quickly distribute heat throughout a metal, throughout a pot. So you'll very often see copper-clad pots. Copper is very expensive, a little too expensive to make a whole pot out of, but you'll see them put it just on the bottom of the pot. The reason for that is, with a low specific heat capacity, it can very quickly heat up and then start transferring heat energy into the substances that are in the pot, such as food, and it does it in a very even manner. Iron, a lot of cast iron skillets out there. We know that iron is a little bit better at retaining heat than copper. It has a higher specific heat capacity. Now we look at aluminum. You don't tend to think of aluminum necessarily as being better than a cast iron skillet at holding heat, but part of that is just because aluminum, it has a higher specific heat capacity, but also it tends to be a less dense metal. So if you compared the densities of those, iron heats up quickly and then dissipates that heat quickly, but it's more dense, so it does trap heat a little better. The aluminum takes a little bit longer to get hot, but then it holds that heat. So aluminum has also been a favored choice for cookware. Okay, so those are all different metals. Now they've thrown in a couple of liquids here. Here's ethanol. So this is ethyl alcohol. This is the kind we drink, so this would be your vodka or whatnot. You can see it has a much higher specific heat capacity than any of these other substances, any of these metals. So even though we think of ethanol as being very flammable, if you're just gently heating it, you're going to have to put a lot more heat in to get the temperature to rise in that ethanol. And then notice this last one, the one that's highest on the list, water. And water is truly amazing. Not only does it have the highest specific heat capacity on this list, it's one of the highest specific heat capacities of any substance that we have. Water has some really amazing properties, and we're going to be talking about those and looking at those throughout the semester, but just keep that in mind. There's a reason we use water in everything, and part of it is just because it's the most abundant, it's everywhere, it's cheap and easy to use, but also it's got so many really unusual and wonderful properties. Water is not like any other liquid that we know of on the face of the earth. And so we'll be exploring some of those great properties. But this is one, really high specific heat capacity. So it takes a long time to heat water up. And anybody who's ever had a pool knows that. You open that pool in the spring, you fill it with water. It's going to take a long time for the sun to warm up that water. For the first few times you jump in there, it's kind of, tooth chattering. You're kind of shivering for a little while until that water warms up. And conversely, if you've ever boiled a pot of water on the stove, you boil some pasta, you take the pasta out, and then you wait for the water to cool down before you pour it out. It takes a long time for that water to cool down enough before it's not still kind of scalding water. That's all because of this heat capacity. Water has an amazing ability to absorb energy. All right, now there is an equation that relates all of these quantities that we've talked about. There are examples in your book that it walks through and does calculations on those. I do want you to be familiar with this calculation. This is an important one, but we're not going to dive into that right now. We want to focus on a little bit of other stuff. We want to get into chapter 4. So I'm just going to show you this equation right now, but I'm not going to hold your feet to the fire, so to speak, on actually using this one. But be aware, the equation that relates those quantities, heat, which is usually abbreviated as lowercase q, is the amount of heat given in joules. Heat is equal to the mass of a substance in grams, so small m, times specific heat capacity, which is being abbreviated as capital C here, that is joules per gram per degree Celsius, times the change in temperature. Right, now see this symbol right here, this delta? You will be seeing that often throughout your chemistry career. Anytime you see a delta in front of a unit, it means the change in that unit. So what this is telling us is we don't want just a temperature, we want the change in temperature. So for instance, if we are going to boil water and the water started out at room temperature, so it started out around 25 degrees Celsius, and we heated it up to boiling, which is 100 degrees Celsius, the change in temperature of that water was 75 degrees Celsius, the 100 minus the 25. Let's look at just a quick example of how you would use this calculation. All right, so this one is talking about gallium. And if you've never seen or heard of gallium, it is an element from the periodic table. It is a solid metal. It is really amazing stuff. There are all sorts of videos out there about people holding gallium in their hand or making a spoon out of it and stirring it in water. The reason they do this is because it's a solid at 25 degrees Celsius, which is room temperature, and it melts at 29.9 degrees Celsius. Now remember, body temperature is 37 degrees Celsius. So if you take that piece of gallium and you hold it in your hand, it'll turn into a puddle of liquid in your hand. And then you can pour it out on the desktop, and assuming you're not in a really hot room, it will re-solidify into a little solid puddle on the top of a desk or something. So a lot of fun to kind of play with and watch. It's not readily available, so we don't have any, but I'll try to put a video kind of showing the use of gallium up on the website somewhere. Alright, so in this case, they're saying that they have a piece of gallium that is 2.5 grams. So if I put a 2.5 gram piece of gallium in my hand, how much heat does it have to absorb from my hand to raise it from the 25 degrees Celsius to its melting point at 29.9? Alright, so if we look at what we're given, we've got 2.5 grams of gallium. We know that it is going to start at 25 degrees Celsius. We're going to end it at 29.9 when it melts, and then we need one more piece of information, which is specific heat capacity of gallium. That can be looked up from a table or off the internet, but here it's given as 0.372 joules per gram per degree Celsius. Now, from all that, what we're trying to find is the heat energy, the Q value. Okay? So, solution map. We go to our formula. Q is equal to M times C times delta T. I have 3 of those. I can use that to get to what I'm looking for, which is Q. So here is the solution to that. Here's my heat capacity. Here's my mass. I need change in temperature. I have an initial temperature, 25 degrees, and a final temperature, 29.9 degrees. So the change in temperature. Now let me point out, not only is delta T the change in temperature, but it's always going to be the final position minus the initial position. So even if these had been the other way around, let's say my gallium had started at 29.9 and ended at 25, then I would flip it around the other way. You can have negative delta T's. The change in temperature can be negative, which just means that energy was going out of it, it was cooling down. Alright, so units become very important in these. I can have a positive Q or a negative Q. But in this case it's positive because I started at 25, I ended at 29.9, so subtracting those out, I had a change of a positive 4.9 degrees Celsius. So now I take this number, sorry about that, this number, and this number, and I plug them in. So M was 2.5 grams, C was 0.372 grams per degree Celsius, okay? And there's joules here. So I'm sorry, I don't know why the joules got left out. This one up here should be a joule times the 4.9 degrees Celsius. Degrees Celsius cancel out here and here. Grams cancel out here and here. The joule that should be up here remains at the end. So now I take 2.5 times 0.372 times 4.9. and I find that it is 4.557 joules. Now, remembering my significant figures, I go back and look. I'm doing just multiplication. This one has 2 significant figures, this one has 3 significant figures, and this one has 2 significant figures. So final answer has only 2. Okay, so 1, 2, cut it off right here, and then the 5 rounds the 5 up to a 6. So the 4.6 joules would be the amount of heat I would need to get the temperature of that gallium up to the melting point. Now, if I wanted to melt the gallium, so that's just getting it to the point where it can start melting. If I want to actually convert it from a solid to a liquid, I actually have to put more energy into it. And it's telling us right here, an additional 200 joules would be needed to actually melt it, to get it from the solid state to the liquid state once it reaches that point. And that's because of something known as the heat of fusion. We're not going to get into that right now, but that is a fantastic way to look into the amount of energy that's needed, not only to change the temperature of something, but then to undergo a phase change, to go from a liquid to a solid, or from a gas to a liquid, or down the other way on any of those scales. Okay? So just to kind of reassure you, I'm not going to ask you to do any of these kind of calculations right now, but I do want to start showing you these kind of calculations, because these are the ones we're going to get into pretty soon once we start talking about the elements in the periodic table and start using the values from the periodic table to carry out some calculations. Right now we're just looking at simple mathematical formulas. Alright, so that wraps up Chapter 3. And there will be some slides available in the non-narrated PowerPoint that list the learning objectives and the goals for this chapter. I'm not going to include those in the narrated previews anymore, just because I think you can go look at those on your own. And the next chapter up will be Chapter 4, and we'll start talking about that.